Have you ever wondered why a straw looks bent when it's in a cup of water? If you have no idea what I'm talking about, go grab a cup, put some water in it. Has to be clear because you need to see what's going on inside the cup, and put a straw inside, or a pencil or a pen, whatever works. And look what happens to the straw or the pencil as you go from air into your cup of water. Does it look bigger? Does it look smaller? Does it look like it's cut in half? Does it look like it goes straight down? Are you able to position the straw or the pencil in such a way that the straw looks like it is going straight down? Or are you able to position it so that it looks like it's cut in half? This is a law of refraction. So when you have waves, these waves in particular, we are talking about going from one medium into another. So as you go from one medium into another, and the different mediums that we are going to be talking about are found in your reference table. It could be air, water, glycerol, oil. It could be anything. Going from one type of substance into another. When this happens, your wave bends due to a change in the speed of the wave. So as you see in this picture here, you have your two different mediums. These are separated by color. So you have this white medium on the top, this yellow medium on the bottom. You have your normal line directly down the middle. Always, we have our normal. And if you remember from when we talked about reflection, your normal and your surface form a perpendicular angle. So your surface is straight across. Your normal must form a perpendicular. So that's what this line is right in the middle. So we have this incident ray, our regular incident ray that is coming in to our boundary. And we know that this is our incident angle right here. And as this incident ray comes into our boundary, it is going to bend as it goes through. And you see how your angle I up here is different than the angle R on the bottom. And this is because the ray, as it bends, is going to produce a different angle. So the speed of these electromagnetic waves, that's what EM stands for, electromagnetic waves, depends on something that is called the index of refraction. And the index of refraction is found in your reference table. On page 2 are the index of refraction values. And the index of refraction, we use the letter N as in Nancy, to be able to denote the index of refraction. The index of refraction is like a ratio, so we do not have any units for it. If you are going from one index into the same index, meaning that you're going from air into air, or water into water, or oil into oil, you have no change. Meaning no change, your wave is not going to bend. You have no change in your direction or in your wavelength. If you're going from a low index to a high index, meaning if you're going from air into water, you're going to travel from a fast speed to a slower speed. And your wave is going to bend towards your normal. If you think about it, if you're going from air into water, water is much more dense than air. So you're not going to have as much room to travel. In fact, it's going to be less of an angle that you'll be able to travel. So your wave will bend toward your normal line. And in this case, your wavelength will decrease. If you're going from a high index to a low index, in this case, you're going to be able to speed up. So for instance, if you're going from water into air, you have much more room to travel, much more room. Your molecules are much more spread out in air. So you're able to spread out go even faster, spread out farther. So you bend away from your normal. And in this case, your wavelength increases. Make sure you jot this down. These rules are definitely important. So to be able to solve for refraction, we use something that is called Snell's law. This is the law of refraction. And here this says N1, which represents your index of your first medium, multiplied by sine of your first angle, is equal to the index of your second medium multiplied by sine of your second angle. Make sure your calculator is in degrees to be able to solve the problems. We also have another formula that we're able to use. And this formula is when we use this when frequency is constant. So you notice in all of these in the formula below, you don't have frequency here. So if you're not given frequency, we're able to go ahead and use these formulas. Notice with this, the location of the 2's and the 1's. It's important. Just like when we talked about the impulse formula or the power formula, where you have multiple formulas that are merged together in an effort to kind of save space, but also to show the relationships between here. Remember, an equation only has two sides, right? Separated by an equal sign. So if you're looking at this particular equation, you need to make sure that you're basically eliminating one piece, right? One component. So if you are talking about the index of refraction and want to relate it to speed, then you would use the first two, the n2 over n1 equals v1 over v2. Say you have the index of refraction and wavelength. Well, then you would eliminate the second, the v1 over v2, so your formula would look n2 over n1 equals wavelength 1 over wavelength 2. It just depends on what's given to you in the problem. Remember, you can literally take your hand, your finger, whatever, cover up one of those, one of the pieces of your formula and get rid of it if you don't need it. So here's an example. We have a ray of light with a frequency of 5 times 10 to the 14 hertz, moves from air into a piece of flint glass. The ray strikes the glass at an angle of 50 degrees with the normal. What happens to this ray of light? Okay, so first of all of these values, N1 and N2, it's given to you right here. However, we are going to use the reference table in the future to be able to find just exactly where these are coming from. So you have crown glass, flint glass. Just make sure you choose the correct type of glass that you're working with. So you're going from air into flint glass. You see that your index of air is 1.0. Flint glass is 1.66. That tells you that you're going into a much more dense medium because you're going into a higher index. Okay, so we have our ray coming into our boundary. We make sure we draw the normal so that we have theta 1. This is our angle of incidence. When we travel through, you will never have a situation where the wave kind of like moves backwards. It will never end up in this section. It always has to pass directly through. It may not look like a straight line. It just looks a little bent, but it shouldn't look like a crazy, like big angle or anything like that. It must be directly through where your incident angle started. So in order to go through and figure out what is happening here, we already know that we have reflection. Always. We always have a reflected ray. So this is where this blue line comes from. So the red, our incident angle is coming in, or my incident ray for that matter is coming in. My blue shows my reflected ray. Now we need to worry about what happens with our refracted ray. And we know, again, that I'm going into a much more dense medium. So that means that I don't have as much room to move out. So I'm going to bend toward the normal. In addition, we're able to go ahead and we can actually go through and solve for what the angle actually is. Now, if we were in school, we would go ahead and we would do this and draw them and use protractors. For now, we're going to stick with the math. And we're going to just make sure that you're able to do the math for these. So we have our formula N1 sine theta 1 equals N2 sine theta 2. N1 and N2 come directly from what kind of material or substance you have. So N1, that's where we get our 1 from. N2, 1.66, comes directly from what flint glass, our index of refraction is. Sine of 50, because they told you in the problem that you had an angle of 50, and we're looking for sine of theta 2. Go through, solve for theta 2, and we get 27.48 degrees.